Welcome to The Explainer. Today, we're going to dive into one of the most important steps ever taken in understanding the atom. It's a great story, actually. It's got a fatal flaw, a mysterious fingerprint, and one brilliant idea that completely changed physics forever.
So, you ever wonder what gives fireworks those amazing colors? Well, believe it or not, the answer is wrapped up in a puzzle that had scientists totally stumped over a century ago. It's this deep mystery hidden right inside the atoms that make up, well, everything.
All right, so let's get into it. Our story kicks off with what was, the main idea about the atom back then. It was a model that seemed to make perfect sense, but it had this massive, universe-ending flaw. So this was Ernest Rutherford's model. I mean, he just discovered that the atom has this tiny, dense nucleus at its center. So picturing it like a little solar system, it just made sense. Simple, elegant, something everyone could picture. But, yeah, there was a big problem hiding in plain sight.
See, here's the crucial difference. Planets, they're electrically neutral. But electrons, they have a negative charge. And that, in the world of physics, is a huge deal. Making a charged particle go around in a circle, well, that sets off all kinds of alarm bells. And here's why. According to the physics they knew back then, an electron orbiting like that is constantly accelerating, right? And an accelerating charged particle has to give off energy. It radiates it away. So as it loses energy, it should slow down, and its orbit should get smaller and smaller until, bam, it spirals right into the nucleus. We're talking in less than a trillionth of a second. Every single atom in the universe should just collapse.
So yeah, why are we all still here? That was the massive, glaring problem. If the known laws of physics were the complete picture, nothing, not you, not me, not this planet, should exist. But obviously, atoms are stable. This was a huge contradiction, a puzzle that the planetary model just had no answer for. They needed a new clue, and they needed it badly. And that clue? It actually showed up from a totally different field of study. It came from looking at the strange, really beautiful light that elements give off when you get them super, super hot. So scientists like Robert Bunsen, of Bunsen burner fame, and Gustav Kirchhoff started using these things called spectroscopes to analyze that light. Basically, you take the light, pass it through a prism, and it splits it into all its different colors. And they were expecting to see something pretty familiar. What they expected to see was a full, continuous rainbow. A complete smear of color, just like when sunlight goes through a prism. But that is not what they saw. Not at all. Instead, they got just a few super sharp, distinct lines of color with big black gaps in between. It was just bizarre. And it got even weirder. Every single element had its own unique pattern of lines. Hydrogen had its set, helium had a different one, sodium another. It was like a barcode or a fingerprint made of light. And this was a massive clue. The pattern for hydrogen, the simplest atom there is, that turned out to be the key that would unlock this whole thing. And this is where our main character, Niels Bohr, a brilliant young physicist from Denmark, enters the story. He's the one who looked at these two huge puzzles, the atom that shouldn't be stable and these weird light fingerprints. And he realized they weren't separate problems. They were two sides of the very same coin. So in 1913, Bohr put forward this totally radical new model for the atom. It was an idea that could explain both why atoms don't just collapse on themselves and why they give off these weird, specific patterns of light. But to do it, he had to suggest a new rule for the universe that was pretty strange. His solution was the foundation of what we now call the quantum model. But honestly, a really great way to picture what he was proposing is to think of it as a quantum staircase. Now, this was the core of his revolutionary idea. Bohr basically said that inside an atom, an electron's energy isn't, continuous. It can't just have any random value it wants. It's quantized, which is just a fancy way of saying it can only exist in very specific, discrete amounts. Think of it like this. Energy isn't a smooth ramp you can stand anywhere on. Nope, it's a staircase. So just imagine the electron is a ball on this staircase. It can be on the first step, or the second step, or the fifth step, but it can never be in between the steps. And here's the magic trick. As long as it's just sitting on one of those steps, it doesn't lose any energy. It doesn't radiate. And just like that, the stability problem is solved. The atom doesn't collapse. Now, if it wants to lose energy, it has to jump down to a lower step. And when it makes that jump, it releases a very specific packet of energy, a photon of light. And suddenly, everything clicked into place. Those unique fingerprints of light, they were the direct evidence of this quantum staircase. Each colored line corresponded to a specific jump. The red line in hydrogen spectrum, that's the light from an electron jumping from the third step down to the second. The blue-green line, that's a jump from the fourth step to the second, and so on. It was brilliant. Bohr had solved both mysteries in one go. So was that it? Was the case closed? Was this quantum staircase model the final correct picture of the atom? Well, no, not quite. Look, the model was a huge, monumental success. I mean, it explained why atoms are stable, and it perfectly predicted the light spectrum for hydrogen. But it wasn't the whole story. It started to break down when you tried to use it for bigger atoms with more electrons. And we also know now that electrons don't really travel in these neat, perfect little orbits. So you can think of it as a brilliant first draft, but not the final book. But here is the most important thing to remember. Even though the details of Bohr's model turned out to be, not quite right and were eventually replaced, its central idea that energy inside an atom is quantized, that was absolutely 100% correct. That idea is still a fundamental pillar of all of modern physics. And that brings us to a really cool point about science. It's not always about getting the answer completely right on the first try. It's about taking these bold, creative steps forward that move us closer to the truth. Bohr's wrong idea was actually this incredibly important revolutionary leap. It was the necessary step that pushed physics into the bizarre and amazing world of quantum mechanics, a world we're still trying to fully understand today.